Hi, welcome back. So this is the second part of the measurement and errors video. Today we'll be talking just about uncertainties, maybe 10, 12 minutes. So go through the video, understand it, and then you can practice as many questions as you can. So just going through this. Now, uncertainties, what is the cause of uncertainty? So whenever you're doing any measurement or you're taking a reading, it results into an uncertainty because you cannot be too sure about the exact values. So to be try to become as closer to the measured value, we do take into account the uncertainties. Sorry about that. So reading and then the measurement. So first, we'll talk about what is what how do you calculate or how do you take into account the uncertainties in a given reading. So let's say, for example, you're taking a reading from a thermometer or a ruler or a voltmeter or an ammeter. So if it's an analog one, the resolution, the smallest value that it can measure, that is the uncertainty. So, for example, you are measuring using a ruler, you're measuring 2 centimeters, and the smallest it can measure is 1 mm. So, you're just converting into centimeters. So, this is plus or minus, this is my uncertainty. Resolution, this resolution of an analog instrument is the resolution. What is resolution? The smallest value your analog instrument can measure, that is the resolution. So we got it. That is my uncertainty. If it's a digital one, so you have, let's say, a digital voltmeter or a digital ammeter, or you're taking a digital thermometer. So if you have a digital one, the increments that a digital ammeter gives, let's say, for example, it measures 2.1 volts, 2.2 volts, 2.3 volts. So zero point 0.1 would be the uncertainty. If, for example, your voltmeter is giving you 2.12, 2.43, so 2.65, so my uncertainty, so in this case, is 0.02. So the increment that your voltmeter or the digital device or instrument is giving you, that is the uncertainty. Now for the measurement part. The measurements, let's see how you're using those readings. For example, let's start with the simplest one. You're using a thermometer to take some readings. Let's say the readings are 1 degree Celsius, 1.1 degree Celsius, and 1.2 degree Celsius. Okay, so now you want to tell what's your temperature. So you've taken the reading, but you want to tell what's the temperature. Now, because you've taken 3 readings, the mean would be your temperature. So in that case, but what's the uncertainty? You calculate the range, and the half of the range is uncertainty. That's it. That's what your exam boards want you to know. Okay. So the half of the range of a given readings is the uncertainty. Second kind of range is, let's say, for example, I have some examples here. Let's say you've taken a length, and this is the uncertainty. Now it's asking you the percentage uncertainty in the length. So the percentage one is just take the uncertainty in the reading divided by the original, the value which you've read, times 100. That's the percentage uncertainty. What's the absolute uncertainty if the length is doubled? So if you're doubling the length, the uncertainty would be doubled. So 2 times 0.02. Any kind of measurements, any kind of usage of that data would always increase the uncertainty in the reading. Let's try another one. Now, you have taken 2 readings, length 1 and length 2, but you've used maybe different instruments. Looks like it's a different instrument. Now, the total length. So the absolute uncertainty would definitely increase. So this is generally used to show the change. So that's the uncertainty. So that is 0.01 plus 0.02. That's 0.03. That's your absolute uncertainty. Now, instead of absolute uncertainty, if it asks you calculate percentage uncertainty, That's not difficult, isn't it? Have we know that? So the percentage uncertainty would be 0.03 divided by, let's say the total length would be 0.80 plus 1.25. That would be 502.05. So divided by 2.05 times 100. Absolute divided by the measured times 100. Done. Simple. Okay. This is a fairly easy topic, but so if it's easy, that simply means you can't afford to lose your marks on this one. This has to be a 100% gain on this mark. Okay, we will try and solve the actual exam questions of different boards in the coming videos, but for now we're just focusing on the concept. Now if you're combining uncertainties, now what are we doing here? We're using the measure red values to calculate the density. So obviously now the density is divided by mass and volume, which is, you calculate the density first. So my density is 3 grams per centimeter cube, but I do not have the error in the measured value of density. So what we do now is, whenever you have a division or multiplication, you cannot handle with the absolute uncertainty. You cannot just divide zero point 0.2 divided by zero point 0.1. That would be wrong. So what you do is you calculate percentage uncertainty first in mass. So that's the percentage uncertainty in the mass, zero point 0.2 divided by 12. Then you add, it's in division, but you still add. It be 0.1 divided by 4 times 100. So that would give you your percentage uncertainty in the density. Percentage uncertainty in the density. I'm hoping I'm making myself clear. Now, so this would be, I'm just 20 divided by 12. So just use your calculator and do it. Now, for example, if you have a question like force equals or momentum equals mass times velocity, mass times velocity, not volume. Okay. Now mass in that case is, I'm taking the same mass, 12 plus minus 0.2, and the velocity is, just making it this way so that you don't get confused with the volume, is, let's say, 6 plus minus 0.5. Now you calculate momentum using 12 times 6, done. 72 kg meters per second. No, so this is grams. So grams meters per second. But now how do you calculate the percentage uncertainty in the momentum? Is you calculate the uncertainty in the mass divided by this. Then you add zero point 0.5 uncertainty in the velocity. That's it. Remember, multiplication or division to calculate the uncertainty in your required measurement, you have to add the percentage uncertainty in the quantities given. You can pause, do it again, or come back again to this one. Okay, let's do another one. If you have repeated readings, measure the values of a wire several times and obtains value between this to this. Now what it is giving you, it's giving you a range. So the range of the reading is 0.08. Say the absolute uncertainty is the range divided by 2. Why do you repeat? To increase or decrease the repeated errors, or to decrease the random errors. The graphical uncertainties, some of the examples ask these questions, and even if it doesn't, that's a simple concept we all should know. If you have a straight line graph plotted to determine the gradient, how maximum and minimum gradients are used to estimate uncertainty in the gradient. So this is exactly same as range. So when you have maximum and minimum gradient, that would give you the range. So the range of the gradients would be maximum minus minimum, and then it just was divided by 2 to calculate the uncertainty. The range of any readings divided by 2 gives you the uncertainty. Why the uncertainty in the gradient may be large? What do you think? So let's say if I have this kind of graph, This is the maximum and this one is minimum. Why do I have the large uncertainty? It's because it's scattered all over. So if you have a scatter graph, yeah, so it's there's no, or maybe you do not have enough readings. So that could be the reason. Not enough readings, not enough data. Okay. Now, resolution and uncertainty. Let's just read. A digital voltmeter displays a reading of this much. So now, absolutely, the the increments is happening in this. So that's your absolute uncertainty. Suppose if it gives you 4.65, it'll be 0.05. If it gives you 4.78, 0.08. Do we get it? Yeah. Okay. How the resolution of the instrument affects larger the resolution, the smallest possible value something can measure, it's just going to decrease the uncertainty. So larger the resolution, less is the uncertainty in your measured value or read value. Let's see this one. This is it. This is an important one. So when you have powers in any red value, how does your uncertainty propagates to the measured values? Now this one, always remember, if there's a power, that power always goes into the multiplication. So percentage error or percentage uncertainty in the time period is 2 times the percentage uncertainty in the length. So this is 2%. So my R error is 4%. Let's try another one. Let's say my kinetic energy is half mv squared. Now the error, the percentage it's given, the percentage error in mass is 3%, and the percentage error in velocity is, let's say, 5%. Now it's asking what's the percentage error or percentage uncertainty in kinetic energy. So it's simple. This half is nothing. The only error that comes is from the mass and velocity. So my percentage error or percentage uncertainty in kinetic energy is the percentage error in mass plus, because mass does not have any power, the power of velocity is 2. So 2 times the percentage error in velocity. So this becomes 3% plus 2 times 5%, that is 10 and 13%. Do we get it? The powers always get multiplied when you're calculating the percentage uncertainty. Where does this come from? This comes from differentiation, but we don't need to know that for now. The significant figures and uncertainty, a calculated value has da 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 da. Explain why this value is not appropriately quoted. Why is this not too many significant figures? How can this be appropriate? So the answer is that too many significant figures. So when you write now, here's a hint. When you're writing your exam questions, doing your exam papers, and you're writing your answers, do not write your answer like this because it's too many significant numbers, not appropriately quoted. How would it be reported? With reference to, say, let's say that's how, with reference to uncertainties. Always take care of the uncertainty. I'm not talking about estimation, don't get worried. Told you we'll be talking only about uncertainties today. So that's it. Just to recap, let's just see. Whenever you have the most difficult one, absolute uncertainties are just added in addition or subtraction. When you're adding two physical quantities or you're subtracting two physical quantities, the final uncertainty will always be added. If you're multiplying or dividing, you calculate percentage uncertainties and you always add them. If you have a power, the percentage uncertainty will always be times. That's it. That's all. All right. Just go through the previous video on errors in measurement and then this one, and we're done to the first topic. Thank you.